So I think there was a question about one of the homework problems. So let's see. So let's do problem 2 first, okay? Because that's more related to the homework problem. Um, so in this case, it said that the blood flow is flowing to the left at 10 centimeters per second, and it appears as blood flowing to the right at 6 centimeters, okay? So it doesn't matter, we don't know which is right or left in terms of, but we can think about, blood flow is obviously past the 180 mark, right? And this is, say, the 10 centimeter flow, right? Okay? And what we're saying is it appears as 6 centimeters. Did everyone see that? Okay, so we went past the halfway mark, so 10. And so what must be the halfway point here? How many centimeters per second must the bank be here? 8. Okay, so if you apply the same sort of thinking to the homework problem, that's all you have to do. Okay, it's literally just how big is the circle and how far around the circle did you go. All right, is that any questions about that? Yes.
Why is it beyond the 180 mark for 10 centimeters?
Basically because we've said that it was going to the left, but it appears it's going to the right. So we know we must have passed the 180 mark.
Say that again, I'm sorry, you said because.
Well, it's told that blood is flowing to the left at 10, but it appears that it's flowing to the right at 6. Right? So if it was less than 8 centimeters per second, there would be no ambiguity, right? But since it's past 8 centimeters per second, it's gone past that halfway mark, so we don't know which way it came. We don't know whether you went this way or that way. Yes?
So I get that the time is now 0.8 because you don't want it to be ahead of the middle. But then how do you decide the gradient amplitude based on that?
Okay, so the formula for the bank is what? It's related to G naught T naught squared, right? Yeah. Okay, so basically we want to we want to increase the bank to what? What do we want to make the bank is now equal to 8, right? Currently is equal to 8 centimeters per second. What do we want to increase the bank to so the 10 centimeters per second will appear correct? What's the minimum we could set it equal to? 10, right? Okay. So what we would need to do is we need to, and the bank, if you go to the formula in the thing, is sort of proportional to 1 over this, right? Okay. So basically, and that formula was given in the formula sheet, I believe, for this quiz. So so there, you wanted to go from a factor of 8, you increase by a factor of 10 over 8. So this factor here, the G naught of T squared, must go down by a factor of 8 over 10, right? And so the only combinations that do that are D and F. Okay? So I wouldn't worry about the actual what answers are correct here. The most important thing, at least for the homework, is understanding this picture here. Yeah. Okay, so so what's the circumference of that circle in terms of centimeters per second? I went 10 one way and 6 the other way. So 16 and half of that. Yeah. So it's sort of, I mean, if you think about, like, if you're in a circular maze, right? You could either go one way or the other way, right? Yeah. Question?
So we're assuming that when they say left, it is counterclockwise?
No, it doesn't matter which way. It doesn't matter, yeah.
How can both D and F be true? But can it also be B, D, and F? Do you only care about? So are you you just trying to get something where g times t squared is equal to 0.8?
Yeah. Or it's reduced by that amount. Yeah.
So then how can d and f be true? Is that the same 0.8 t, but their g's are different?
Let's see. Well, one of them, the 10 is just the minimum you have to make it. You could make it bigger than 10, right? You could decrease it more, right? You could bank that's the minimum, but you could always go more than, you could decrease it. You could make it 12, and that would be okay, right? Okay. So anyways, without sort of telling you too much about the quiz, I think if we spend too much time on this problem, it's not going to be advantageous to most of you. So I wouldn't worry too much about this problem for the upcoming quiz, okay? All right? Fair enough? Okay. Go ahead. There's a question?
If you go back, it's just going to be 0 again, right? Or it's going to be the apparent flow. Say the actual flow is 16 in this example where the bank's E. It would just look the same.
It looked the same as, yeah. You wouldn't have any phase.
Exactly. Okay.
Yeah. Unless you had a way of unwrapping phase. Okay. Okay, any other questions? Okay, so let's get on to the other questions, which will be more helpful for the quiz. I was mostly going over this problem to help you with the homework. Okay. So for problem 1, we have a vial with T1 of 1,000 and T2 is 1,000 at room temperature. You raise the liquid temperature to 50 degrees C, which is quite a lot. What are the most likely values for the T1 and T2 of the heated liquid? So with heating, do we increase or decrease the tumbling rate? Right, so we increase the rate, right? So what does the T2 versus rate curve look like? It goes up, right? Yeah. So T2 must go up, right? So we know that these can't be correct. Okay. What about T1? Where do we think we are with T1? We have a liquid, right? So remember T1 is like this, right? So where do we think we are on the curve? Do we think we're to the left or the right? Do we think we're the right? We think we're in this region because we're a liquid, right? So as we increase the tumbling rate, what must happen to the T1? It also has to go up. So that is it B?
Yeah.
Yeah, so the answer is B. Okay. So everyone okay with that? Okay.
Had this been a solid, we would have seen possibly T1 go down and T2 go up.
Yeah, yeah, that's right. Okay, I'm not sure if we did this problem in class, but if not, let's go over it anyways. So this is one of these problems where you just have to think through the spin warp sequence. So you're given the FOV as 24. You're given the maximum available gradient is 5. The user doubles the FOV in the x direction. Okay, so x is always going to be readout, and y is always going to be phase encode. Okay, so he doubles it to 48 centimeters. What will need to change in the pulse sequence? And assume that delta t does not change. Okay, and it says you may pick more than one answer. Okay, was there a question there? Just stretching. Okay. So which of these can't be true right off the bat? A and B, right? Because we didn't do anything to the phase encode direction. Okay. So FOV doubled, right? So what must be true of k sub x, delta k sub x? It's half, right? Delta t is the same, right? So what must be true of g sub x? Yeah, right? The area has to go down. So we know that the amplitude of the radial gradient will be halved. So h is true. Okay. What else do we know? Okay. What about, and it says the resolution is held constant. Okay, so that means wk sub x is the same, right? But delta kx has gone down by a factor of 2. So what happens to the number of readout samples that I need? It must double, right? Okay. And what about the length of the readout gradient? it also has to double, right? Because that's just the number of samples times delta t. Okay? Everyone okay with that? Okay. Again, another spin warp pulse sequence, which actually is almost the same as the last one, but keeps the matrix size the same. Okay, so the FOV went up by a factor of 2, as before, right? So we know that H must be true, right? Because delta T is the same. What about the resolution? What must happen with the resolution? It says the FOV has increased, but the matrix size is the same. Yeah, it goes up by a factor of what? Right, so the resolution size goes up by a factor of 2. So WKX goes down by a factor of 2. And we knew delta KX went down by a factor of 2. We also already know A and B can't be true. So does the number of readout samples change? No. So neither of these are true. And the length doesn't change either, right? Okay, because basically I've changed both the FOV and the resolution. They've both gone up by a factor of 2, so the number of samples stays the same. All right, any questions on that? Okay. Consider an RF pulse of the form A sinc t over t, where t equals 250 microseconds. Select the amplitude A needed to achieve a flip angle of 45 degrees. Okay. So we know in general that gamma times the area is equal to flip angle, right? Let's call that theta. And in this case, that's equal to pi over 4, right? Okay. And the area of a sinc is just gamma times its amplitude times its first zero, t. Okay. And we want that equal to pi over 4. So we're given, so gamma is 2 pi times 4,000 times A times 250 times 10 to the minus 6. And if you solve for that, you get 0.125 Gauss. Okay, so F would be the closest answer. So the key concept there is gamma times area is the flip angle. Okay, consider a slice-select pulse of the form A sinc t over t, where t equals 400 microseconds. Was slice-select gradient need to achieve a slice thickness of 5 centimeters? Okay, so now what we want is to use bandwidth equals gamma over 2 pi gz times delta z. Okay, where bandwidth is just equal to 1 over t. Okay, so we can solve for g sub z equals 1 over t, gamma over 2 pi, delta z. And it looks like if you solve for that, you get 0.125 Gauss per centimeters. So A is the correct answer. Okay, so once again, the key thing to get is this. Yes? Was it on last time's formula sheet? Yeah, I don't think these are going to be, the ones that are really easy to remember are not going to be on the formula sheet. The ones that are more conceptual won't be on the formula sheet. Yeah. Okay. But that's only like a few, right? Okay. Like FOV was that on the formula sheet? It was on? Okay. Well, yeah, let's assume, I'm not sure. I haven't made up the formula sheet yet. I haven't checked yet. Yeah. Okay. Is everyone okay with 6 then? So let's move on to 7. You want to go kx equals 1 inverse centimeter and 2 inverse centimeters. You have 5 Gauss per centimeters to play with. What's the minimum temporal width you can use for these gradients? So first of all, which one of these dominates? Is it kx equals 1 or ky equals 2? Right, that's the farther out in k space, you're going to need more area to get out to that point. So we want gamma over 2 pi times 5 times the time to equal 2 inverse centimeters. Okay? So T is just going to equal 2 inverse centimeters or 5 Gauss per centimeters times 4,000 hertz per Gauss. And that turns out to be 0.10 milliseconds. All right? So 8, you're asked to design a spin warp readout gradient to achieve FOV of 25 and resolution 1 millimeters. The maximum gradient strength available is 5 Gauss. That readout sampling period is 10 microseconds. What should the amplitude of the readout gradient be? So we need to know what delta K is, right? So what's delta Kx equal to? 1 over 25, right? And that's just going to be equal to gamma over 2 pi times my amplitude times my delta t. Right? So I can solve for A is 1 over 25 centimeters, 4,000 hertz per Gauss, 10 microseconds. Okay? And that gives us 1 Gauss per centimeter. Okay, any questions on that? Okay. This one is, let's see, you're asked to design phase and cogradients to achieve FOV of 25 centimeters and resolution equals 1 millimeter. The maximum gradient strength available is 5 Gauss centimeter. What is the minimum width you can use? So for this one, do we want to use FOV or resolution? Which is the parameter that matters here? Resolution, right? Because resolution determines how far out in K-space I go, right? So 5 Gauss per centimeter, that 5 Gauss per centimeter has to get me out to the farthest part in K-space as quickly as possible. Okay? So the resolution is equal to 1 millimeter is equal to 0.1 centimeter. Okay? And so we know WKY is just equal to 10 inverse centimeters. The what? Okay. And then we want to get out to half of that, so ky max is half of that, 5 inverse centimeters, right? And we won't do that with gamma over 2 pi times my 5 Gauss per centimeter times my time, right? So it looks like the time is just going to be equal 1 over 4,000, right? Which is 250 microseconds. Okay, so for this one, the main thing was to realize that it's the resolution that matters. So in these problems, you know, if there is a choice like this, then typically it's just checking to make sure you know that that a lot of times you're given things, maybe you're given 4 or 5 facts, but maybe only 2 of them are relevant, or maybe 3 of them are relevant. So the main thing there from a test taking point of view is to quickly identify what's relevant so you don't spend time doing what's irrelevant. Because if you spend more time on a problem that's meant to be done very quickly, then you don't have time to do other problems. So from a test taking point of view, you just want to sort of identify what's relevant as quickly as possible. Yes?
Can you say again, why do we have to focus on the window?
The resolution?
Yes.
Yeah. Okay. So for the phase and cogradient, you're told that you have the maximum gradient strength you have is 5 Gauss per centimeter, right? So you want to figure out what's the biggest area you're going to need, right? So the biggest area you need is to get out as far in K-space as possible. So that how far you go out in K-space is determined by resolution. So that's why you want to do the resolution. The FOV just tells you what little steps you take, but that's not going to be the biggest gradient you need. Okay? Any other questions? Okay. This one here, we didn't, don't worry about it. Because we didn't get to that in this year. Okay, so this is related to excitation K-space. We didn't talk about enough to get to this problem. Yes?
Is number 9 true for even not spin warp?
9, is it true for not even spin warp?
If it's like a different way of moving through K-space.
Let's see. Yeah, it's generally going to be true because you still have to get out to that Partington space. But phasing cogradient typically, unless you're told it's not spin warp, just assume it's spin warp.
Okay.
Yeah. Otherwise, you'll be told explicitly. And unfortunately, to give anything not spin warp is really too gnarly to give on a quiz because, if it's like non-Cartesian, then you've got to really, it's tough to do, tough to grade, not a good thing for a quiz. Okay.
Question.
Yes.
What's the difference between number 9 and number 7? Are they asking for the same thing, or am I understanding this wrong?
They're basically the same thing, calculation you do at the end. It's just that in number 7, you're given where you want to go, the 2 inverse centimeters, right? You're given that. 9, you have to figure it out. You have to figure out that you want to go to 5 inverse centimeters.
Oh, okay.
So there's just 1 or 2 more steps in number 9 versus number 7.
Is 2 centimeters, is that KY max for number 7? 2 inverse centimeters, would that be KY max or would that not be?
Well, you don't know why you're going out to that. So someone might just said, I want to go out to that point. So it doesn't have to be KY max. Yeah. Okay. Any other questions? Okay. Let's look at number 11.
Oh yeah, Professor. I think
Yes.
the emails are on Flutter.
Oh, okay. Let's see. Is that good? Okay. So number 11 is takes a little more thinking. So let's quit the emails. Okay. So it's saying that you have a readout gradient of 0.1 Gauss per centimeter. The sampling period is 10 microseconds. Desired resolution is 1 millimeter. You have an object at F equals 0. Okay. But this object is off resonance, which means it's already processing at 100 hertz. Okay. So if it's at isocenter, no matter what gradient you apply, there's no added field, so it shouldn't have additional precession. Okay. So when we reconstruct an image, this object will appear to occur somewhere else because it'll appear to be some other spin that's processing at a higher frequency. Okay. So then the question is, how far does it appear? Okay. So the key here is to think about gradients. What do gradients do? Okay. Gradients cause things to process at faster or lower rates. Okay. In this case, you're told you have a gradient of 0.1 Gauss per centimeter, right? So the question is, how far off do you have to go for that spin to process at 100 hertz? Okay. So you just say that, okay, there's 0.1 Gauss per centimeter. That's my gradient, right? And I know there's some delta z that I'm trying to solve, okay? And then I have to multiply that by gamma over 2 pi, which tells me sort of precession per unit Gauss, okay? So I'm saying I want all that to equal 100 hertz. Okay, so delta z is equal to 100 over 4,000 over 0.1. So that gives me what? 1,000 over 4,000, 0.25 centimeters or 2.5 millimeters. The what?
The part about the isocenter.
Okay. Isocenter is x equals 0. So gx times x is equal to what?
Like the delta V at that point, right?
Well, what's gx times x? It's 0. Yeah. So there's no added field at x equals 0. So isocenter is defined as the origin where the gradients don't have any effect. Right? Because gx...
I just want to understand what the third last sentence means. Like, I mean, I understand the first, but the object exhibits off resonance means that it's processing.
Yep.
But what is the second half of that sentence? What do we get from that?
It's just trying to help you. It's just saying that assume it's higher than what the Larmor frequency should be at the isocenter, which should just be B naught. Yeah, so this should just be B naught, right? Okay, any other questions? Okay. So the last multiple choice, Dr. Block designs a saturation recovery T2-weighted sequence to differentiate between two liquids A and B with T2 values of 1,000 and 2,000 respectively. Okay. He had some gelatin to liquid A. What should Dr. Block do to keep the image contrast approximately the same? Okay. So what's going to happen with the T2s of these tissues? Is it going to go up or down?
Oh, down.
Yeah.
Is it going to go up or down?
T2 is going down.
Right. Because remember, we have this curve, right? Rate. So as things become less mobile, they're going to go down. Is that okay? All right. So so basically, and we know that as we talked about at the beginning of class today, if I have two species, the optimal T is probably the average of those two, right? So what's going to happen to the average of those T2 values? Also going to go down. So I want to decrease TE, right? So I can get rid of these guys. Okay. So now, let's see. Okay. So then, let's see. The TR, okay. So now we can either decrease TR or increase TR. And what's happening to the T1 of these guys? The T1 is probably going up, right? Or decreasing, right? It's probably decreasing, right? Yeah. So we might be tempted to say we could decrease TR, but we're actually not told enough to know whether we're at the optimal TR or whatever, okay? So we're not told, so the TR is probably long enough, and so we probably could decrease TR, but I think the answer was increase TR, right?
So do we increase TR just because we want to have a long TR for like a T2 weighted imaging, or?
I think the thing is that for this one, looking at that now, yeah, I guess the way that it's read it, it's basically to keep the image contrast approximately the same. I think if you assume you're already sort of at infinite, at a very long TR, such that it's purely T2 weighted, then you know, increasing TR will keep you there. Okay, but if you were asked, you know, what would be more optimal in terms of scan time, then if you were added that component, then possibly decreasing the TR would be better. So it really depends on what you're asked. So in this case, since the image contrast the same, if you had to pick one, you would pick D because you know you can't go wrong. Okay. All right, but this could be correct if want to minimize scan time.
For the exam, if we select B and D and explain why we select B and D, and there's a chance for both of them to be right, would that be okay?
Yeah, I mean, I think that's when I write the quiz, I'll try to minimize that, but sometimes it's difficult to avoid that. So if that comes up, then we would certainly adjust for that. Okay, any other questions on the multiple choice before we move to the Fourier response? Okay, so this one, in this year, I mean, you know, the Fourier response was arguably more than in the 2018, right? Because you're actually asked to generate things that are not just multiple choice. So so I would say in terms of preparing for the upcoming quiz, it's not that the Fourier response will be like this one, but just it will be sort of certainly, and it's not that the free response will be the majority of the quiz, but it's just more there will be some free response that does require a little more sort of thinking about the principles. The math behind the quiz is meant to be very easy, so if you find yourself doing a lot of math, then that's not correct. That's a sign to stop. And so you want to really just, if you have trouble, maybe skip to something that's easier and then come back and sort of really just, the problems are just sort of meant to force you to really think about the principles, okay? So let's do this. This one is actually a little more plug and chug. First you're asked to derive an expression for the object using the Rect and Cosine functions, okay? So this is my object here. So let's do the easy part first. What's the width of this object? 4. And what's the width, the height? 4, right? So I know I need to have a rect of x over 4 and a rect of y over 4, right? So that's the easy part, all right? So now the hard part is what kind of cosine is this, right? So it's going to be a cosine of 2 pi. And what's the period in the x direction? Right. So kx must equal what? 1/2. It could be plus or minus 1/2. We don't know yet, but it doesn't really matter too much right now. So let's just say it's 1/2. So 1/2 x plus, what's the period in the y direction? 4, right? Because this is the period, right? So now ky, is it plus or minus 1/4? It's, yeah, how do we know whether it's plus or minus 1/4? Right. So it is minus 1/4, and if you're not sure, let's say we put in the minus 1/4 here. So it's minus 1/4 y, right? So one way you can think about it, there's a couple ways you can think about it. One is, where is the line? This is an equation of a line, right? 1/2 x minus 1/4 y. When the phase, there's a line where the phase is equal to 0, right? So let's look at that line. 1/2 x minus 1/4 y is equal to 0, or y equals, what is it, 2x, right? So, and that looks like the line of 0 phase, right? Okay. The other way to go about it is if you go back to kx and ky, right? We know that if I go to here in k space, the lines are going to go like that. So we know which quadrant we're in. Okay?
How about if your x was negative and your y was positive? So like
Sure, let's say kx was negative 1/2. What would ky equal? Plus 1/4, right? Right, because I could be I'm either here or I'm here, right?
So would that be also
That's fine too.
correct?
Yeah, they're both fine. And because the cosine's an even function, right? So if I multiply the argument by negative, it's the same thing. So they're both correct. All right? Okay. Derive and sketch the Fourier transform of the object. So we know that we're going to have 1/2, delta of kx minus 1/2, ky plus 1/4, plus delta kx plus 1/2, ky minus 1/4, okay? Convolved with sinc of 4 kx, right? Sinc 4 ky, and then there's the 4's come out, so there's also a 16 multiplied by 1/2, so that's 16 over 2. Okay, so that's fairly straightforward. And then if you want to graph that along kx and ky, we have, so this is, say, 1/2 minus 1/4 minus 1/2, 1/4. So the Dirac delta functions are there, right? Okay, and then we have these sinks, and the sinks, the sink of 4kx and sink of 4ky, and so the first zero occurs at 1/4 away from the peak. And so you can just sort of, in this case, you can just draw like little things here. And then you can just indicate, that this is like 1/4 away or something. If it is 1/4, it would look different, but you get it. Let's see. Yeah, so go by what's in the solutions. I didn't draw it very well. Okay, but that spacing is 1/4 away. So, okay. So, are there any questions about that?
So, sorry, the sink functions are centered where?
They're centered around the Dirac delta functions, right?
So it's not 4, it's 2.
Well, this is one is centered at 1/2 minus 1/4, right? One is centered at minus 1/2 plus 1/4, right? So once you know the frequency, right, you know that you're going to have one at 1/2 minus 1/4, and then one at minus 1/2 plus 1/4. Okay. All right. What are the values of delta kx and delta ky needed to avoid aliasing? So that's fairly straightforward. So what are those delta k's equal to? Yeah, 1/4, right? The resolutions are 0.5 and 1. So what are the maximum? What are kx max and ky max? So we know wkx is equal to 1 over its resolution, so that's 2, right? So kx max, which is equal 1, right? And wky is equal to 1. So ky max, which is equal to 0.5. Okay? So one thing about this problem, which is sort of, I guess, good and bad, is that the parts are fairly independent of each other, right? So I mean, you could, even if you get A and B wrong, you could still get C and D correct and do the rest of the problem just fine. Okay. So that's another thing is if you have a multiplier problem, and it's okay to jump ahead and see if there's parts you can answer without answering the. If you get stuck on an early part, it's not that every problem will have everything linked together. So don't make the mistake of getting stuck here, but when maybe you could have done the latter parts of the problems just fine. Okay? All right. Okay, so for example, E, F, and G really require, you basically, like E is relatively straightforward. You're at the center of k-space, right? So just draw the phasor diagrams and compute the vector sum. So here's my object, and let's change the color here. Let's see, let's make it red. So I just do the vector sum, right? I can just draw these vectors everywhere, right? Right, so this is definitely the center of k-space, right? Okay, so this doesn't really appear very good, right? So this is a sampled version of the what we had. So basically, it looks like this is equal to 1. These are 1s, right? And this must be minus 1, right? Is that right? And these are all 0s, right? So we sum along this, and this. That gives me 3 plus 5 plus 3, right? So this is a 3, 5, and a 3, right? And then I get a minus 1 here, a minus 1, 2, 3, 4, 5, a minus 5 here, 1, 2, 3, 4, 5, another minus 5, and then another minus 1. Is that right? Okay. So what do I get at the end? I get 11 minus 12 minus 1. Okay. And then here we're given kx equals 1/2 minus 1/2. Okay. So it's kx equals 1/2, ky equals minus 1/2. This is a period of 2, right? They both have a period of 2. So I would start off by drawing, typically I would do these problems, I'd start off at the isocenter and draw that. And then I know I want to go clockwise with a period of 2, so I draw when that period of 2 occurs. Okay. Halfway between, we know it has to go the other way, right? And then I can draw those, right? And then also this one must point this way, and therefore I can draw these. Okay. So usually what I find easiest on these problems is to draw the principal axes along ky equals 0 and then along kx equals 0. Okay. So we've done along x equals 0, sorry. So this is the x, or sorry, along y equals 0. So y equals 0 is that line that I've just drawn there. Okay. Are there any questions about how I drew that? Okay, so now let's look at going up along the y direction. So we have ky equals minus 1/2. So that means I'm going to go clockwise, right? Or counterclockwise. And here, because of the sampling, it looks like I'm sampling like that, right? So that, oh, sorry, that's a mistake. One period, it's already the period of, let's see, 2, yeah. So I'm here, right? And so this would be there, right? And this would be like that. Okay? So now we know that basically going up and down just multiplies by minus 1 or 1 to whatever we had. So then we can go here and then just, let's see. Is this going to go up then? Does that make sense? Yeah, okay. Up, down. Okay, so does that look right? Okay, so now we just have to sum along the diagonals because all these guys are 0, right? This is 0, this is 0, this is 0. Did I get rid of the wrong ones? And this is 0, right? Okay, so this is going to give me a 1, right? It's going to give me a minus 1, right? This row here is going to give me what? A plus j. Okay. This column here is going to give me what? A lot of things, this cancels that out, that cancels out. It's going to give me a minus 1, is that right? Okay. This is pointing 1 and it's multiplied by minus 1, so it gives me minus 1. Is that right? Okay. This row here gives me what? Does it give me minus 1? Yeah. What about this guy? Minus 1? This guy gives me what? Minus j. And this gives me minus 1. So I have 1, 2, 3, 4, 5, minus 5, plus j minus j cancels out, so I just get minus 5. Okay, and the last one is what? What is the, so this one is sort of, this is related to the other parts of the problem. So what is the, where would you expect the Fourier transform to be maximized for this object? What kx and ky would you want to pick to optimize it? So where is this Fourier transform optimized? Whoops. Yeah, it's optimized at the peak, right? So we could just pick, for example, kx equals 1/2, ky equals -1/4. Okay? So let's do that here. So kx equals 1/2, ky equals -1/4. So once again, the period here is 2. Didn't we just do this? Oh, no, we didn't. Okay. All right. So here we still have the same thing, right, for this one. Okay. But now the period is 4 here. So we're only going to, this is only half a period, right? So this guy is going to be pointing this way and this way. So they're going to be 180 degrees. And we're going counterclockwise, so it's going to look like that. Okay. So in this case, the easiest thing to do is, I usually find it easier to go left to right here. So basically now we know we can just fill in these. So this is going to be up, up, like that, down, down, and then this is going to go like that. All right, so that's going clockwise there, and that's going clockwise like that. Okay, and then the next row, these repeat like that, and this must go like that, and it's going to go clockwise, down, clockwise. Wait, clockwise is not that one, right? Oops. So clockwise would be this way, right? And this one, so clockwise is like this. Clockwise is like this. Okay, so that's the phasor diagram for that one. So let's look at the sum. So this is -1 times 1, so it's 1, right? So this is going to be equal to 3. This is going to be equal to 5. This is 5. This is 5. This is 3. This is 1. So the sum is 15 plus 6 plus 2 equals 23. And that's, if you get an answer like that, that's good, because that's much more than 5 or -1, or -5 or -1 in terms of magnitude. So obviously if you've optimized the Fourier transform, then that should make you feel good that you got such a big number. Okay, so I would say the only comment I would make about this quiz is, you know, I feel it has too much drawing of arrows. So you won't have this much drawing of arrows on the upcoming quiz, because I know this is sort of painful to do. Okay, which is why we didn't do it in 2018. All right, any other questions before we end? Okay.